breaking all the rules. From Newton to Einstein, concepts elevate. Keep the stream, it's the key to our fate. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice. Got the Pythagorean triangles about to flex. Quantum theories on deck, breaking all the specs. Relativity theories, worlds getting small. Grasp the universal laws, standing tall. From the atom to the cosmos, we rolling deep. Gracing up the stars, no time to sleep. Black holes and supernovas, concepts we unfold. Brain power heavy, yeah, that's Dr. Gold. Dr. Gold dropping gems, knowledge raining down. Actual education making scholars all around. Perpendicular minds, angles sharp as ice. Maths and physics, yeah, the future's real nice.
All right, what's up, everybody? There we go. Nice. Let me share my screen. Wait. Yes. Bring back. Share my screen anyways. There we go. I need my chat to work, though. What's up with my chat today? Let me fix that. One sec, it's loading. There it goes. Alright, let me clear this. Oh, those are fake messages. There we go. I don't want to back to that one. Okay. Now I want this. It's not a short. And I want this one. There we go. Okay, now my chat's working. All right. Thanks for the raid earlier, says G. That was super fun. Hope your viewers got to see some. We were doing some physics. We're doing this. This diagram actually is pretty messed up. Graphically how it shows, because it says like it rises 45 centimeters above the bottom of the sink. Okay, cool. And descends 85 centimeters to the pail. But then that means that this length must be 85. Not this. Not to the water level. So this is actually kind of a scuffed picture, to be honest. Yeah, okay. All right. Let's see. This is my last week teaching at UCLA for the summer. So my last lecture is tomorrow. And then they take the final on Friday. And then I got to grade the final. That might take a couple days. But then totally done. It's been such a whirlwind 6 weeks. I'm like, where's the time gone? Anyways. So I'll have a lot more time to dedicate towards you guys, my regular viewers and the Discord. And also the school year, I guess, is starting for normal school time activities. And that's when we start getting a lot more people in the stream asking homework questions and stuff. So it's good timing. Although I'll be gone for about a week. at the end of August, like first week of September. That's Labor Day weekend anyways. It's kind of like a whatever. I'm not gonna be gone for Burning Man. So this week, however, I do want to kind of kick off like the end of me teaching at UCLA by doing something fun. So we'll have a chess tournament, I think, on Friday. I'll announce that today. Give away some prizes, have some fun. Okay. Well, we wait for the UCLA students. Or actually, let me check CampusWire real quick. CampusWire is the website that they all like post their questions and discussions and things. Yes. Same process. Just a couple more questions. Nice. Someone's asking that. Clickers. Just to confirm, no more clickers. No more clickers. I always like putting like little funny memes. Let me think of a funny meme for these guys. Dude, I put "it's finished" and I get like a bunch of like Jesus Christ on the cross. Excuse me?
This guy stinks!
That's pretty terrible. It is finished? I don't know. Is that like a Christian thing, really? Oh, it's Jesus's final words on the cross, where it is finished. Interesting. Oh, I didn't know that. Okay, I learned something. I thought about this meme, the one where Frodo like casts the ring into the fire. I'm gonna copy this image for them. Put it in. Very cool. All right, good. I love this. Yeah, people are asking and answering questions. Great. Good job, people. Okay, let's see. Probably got some questions from yesterday. Let's see what we had. There were some fun ones in here. Wait, this is our website. There we go. What do we have on the queue? This was a good circuit question. If Zanara shows up, I will help out with this one. Let me see the one that David had, right? Let's maybe go through like the work that this one, for instance. Oh, let me delete all these pages. Okay, find the particular solution to the following differential equation: y double prime plus y prime plus t squared e to the t equals t squared plus e to the t, t squared times e to the t, sorry. Okay. I know for something like this, I want to, like, first figure out, like, the particular solution, right? I think it's usually what I do. And then I figure out, like the generic solution, I guess. Is the general solution the main one? Wow, 70 stream streak. Good job, Taco. You've been coming to all my UCLA lectures too? That's crazy. Okay, so I think usually I want to try this with like, let's try the solve for the homogeneous first. I think this is the general strat. Anytime you have just a chill, like, separate... This is kind of, I guess, kind of separable, right? All the Y stuff's on one end, all the T stuff's on another end. I can set it equal to 0 and see what we get. So that would be... You helped me pass, thanks. Thanks, Cubicle. You're very welcome.
Good job.
Oh, I don't know why they didn't show up in my chat. Where'd he go? I saw it. Wait, where'd he go? Oh, you retracted the message. Oh, okay, it's fine. You're good. All right, so let's solve for this one. Y double prime plus Y prime is equal to 0. So instead of solving for... Eventually, we want to get Y squared... Sorry, Y double prime plus Y prime is equal to T squared e to the T. But I'm going to solve for it equal to 0 first, because this is chill. This is where you can assume, for instance, that Y is of the form like Y is equal to like e to the RT. So Y prime is equal to R e to the RT. And then Y double prime, second derivative, right? You pull down another R, would be R squared e to the RT. And so this becomes... This can also be reduction of order. Okay. Oh, I see. So, for instance, you would say that, like, U is equal to Y prime, and so then this is U prime plus U. Interesting. Okay. That's another way to do it, I guess. But wait, can you do reduction of order if it's equal to T squared e to the T? I don't feel like you can do it for that, though. All right. Let's see. So this is R squared e to the RT plus R e to the RT is equal to 0. Notice how you can cancel all the e to the RTs out. So then you get R times R plus 1 is equal to 0. And so this tells me my solutions are R is equal to 0 or R equals -1. So then, like, what is this? Is this like the general forms? We call this like YG? Oh, okay. This would be equal to like C1 e to the 0t plus C2 e to the -1t. So that's just basically C1 plus C2 e to the -t. Okay, now let's look at what Breasticles wrote up. Wait, can I just open it, please? Integrate twice? Yeah, I don't want to do that.
Disqualified.
All right, let's see. All right, so you talk about something called let me see. F is what's called a forcing term. We got to work on your handwriting, Breasticles. I don't know. Is this because you're doing it with a mouse? Or is this you with a stylus? I'm curious. Your handwriting is a little shaky. Yeah, your handwriting is shit. Yeah. It's too funny. Why do we think people have like bad handwriting versus good handwriting? Is it because like you got do students these days not have the class where you had to, you know, have the dotted line and like carefully do the thing in the dotted line? Oh, so it is with a pencil, yeah. You know what I'm talking about? You didn't. It didn't help, dude. Okay, look, they have a cursive handwriting book. No one needs to know cursive. Absolutely, no one needs to know cursive. That's such a. Do they still teach cursive? Taught cursive when I was in school. But yeah, dude. Yeah, there you go. This is what you need, dude. Just follow the lines. Why did the sun go to class? See the progress. No, it's funny. There's stereotypes about handwriting amongst like certain like demographics and like majors and whatever. Doctors are notorious for being like absolutely terrible handwriting. Yeah, like doctors' handwriting. I don't know why. I guess it's because maybe doctors focus on things other than what their handwriting looks like. Yeah. It got worse too as I went to a service because there's barely any friction on the screen. I don't pick up my pen when I write a lot either. Oh, okay. Yeah. So you're just like slurring your words, but handwriting form. Oh, man. Okay. Differential equation LU equals F, where L is any linear differential operator, and F is what we call a forcing term. Then LU is equal to... Okay, so you're calling the differential operator the second derivative plus... What is... Dude, what is this, bro? What? Is that just K? K? Why is it K squared, by the way? I thought it was the second derivative plus the first derivative. Oh, these are just examples. Oh, I see. X. I didn't. Yeah, sorry. I didn't see the X part. Got you. Okay. Great. Okay. We can represent our solution as the following. UP, where U is the solution to the homogeneous. Cool. So that's what we've been doing, right? This is the homogeneous solution. K squared is more... Okay. Okay. And UP is the particular solution caused by the forcing term, right? The forcing term is whatever the equal to on the right side. Two main methods to find undetermined coefficients. This method is glorified guessing. Yeah, that's a lot of diffie-q, man. I apologize. A lot of diffie-q is just fucking guessing.
Oh, no.
Okay. All right. Oh, I see. So if you're saying if it's equal to 1, then y particular is probably of the form A. And if it's of the form... Now wait. YP. Oh, I see. What's the thing on... Okay, this is F is what you're saying. Okay, I got you. F is the forcing term. Got you. Okay. That's cool. I get it. It's okay. It's splitting it across. Okay, so if your non-homogeneous, whatever is on the equal sign looks like one of these things, then this is what it's supposed to be. Oh, okay. So you're going to say that I think this is the one I want. Okay. So then we're saying, okay. But what about the particular solution? It is glorified guessing. Okay. Because we have y double prime plus y prime is equal to, what was it, t squared e to the t? So whatever this is, all right, let's make a different color for it. That's what we're looking here. Looking for these. And so the one that works, I think it's this one. Yeah. Okay, so we're going to guess. YP is of the form ax squared plus bx plus c. And in this case, it would be just e to the t, right? I think I kind of see this, though, right? Okay. So if it's e to the whatever, it's e to the whatever. And that makes sense, right? We've done that before. If it's x squared, it's got to be a quadratic. This is similar to, what's it called? Like partial fractions? Partial fraction decomposition? I kind of see something here. Interesting with the... Okay, so if it's sine of x, you have cosine and sine. If it's a quadratic and then sine of x, you have two sets of quadratics. And then if it's x e to the x, well, now you have the e to the x. You also have, I guess, a linear term here. So interesting. Wait, they didn't do... So they did e to the 5x. Oh, okay, here it is. This is what you're talking about, sorry. This is the... Yeah, this is like the linear. This is the quadratic in front of e to the x. Very cool, actually. I see a pattern. Yeah, if you multiply a function, you just multiply the form. Okay. Cool. Okay, so I'm going to guess that yp is equal to that. But I have some undetermined coefficients, right? So, my guess is I'm going to take derivatives and plug in, and maybe we see stuff that, like... yeah, sorry, this is all at squared, yeah. And there's also an e to the t. Correct. Then e to the t. Okay. All right, let me look at your notes. Let's see what's next. We can sab up. What is this? Dab up? What are you saying here, dude? Gab up? Supplement up? What's this? What's this fucking word here, dude? Oh, sub up. Okay. Okay, and then we'll do variation of parameters. I think I do like variation of parameters better. Okay. This isn't too bad, though. Okay, so then y prime of p will be the first derivative. So this is a chain rule. Sorry, it's a product rule. So I have to do the derivative of the first, which is at plus b times the second, plus the derivative of the second, which is still just e to the t. And then that's going to be at squared plus bt plus c. Okay. The second derivative... Oh, this is getting messy. Oh, I don't like this. I don't like this, dude. Alright, derivative of the first, that's just going to be a e to the t plus e to the t at plus b. Okay. And then plus e to the t at squared plus bt. It'll save some effort if you just call the quadratic v. Yeah, I guess so. Oh, okay. Okay, I think that's cool. I'm a fan of that. Yeah, let's see. Right, you'd call this v. You'd call this v prime. You call this v prime. Yeah, that's a cool trick. Oh, and I screwed this up, actually, sorry. This is 2at, right? Uh-huh. Forgot the derivative of t squared is 2. 2. Okay, and then this is, yeah. 2at plus b times e to the t. Right, and yeah, we could have called this, for instance, v. We could call this v prime. Yeah. But then I need to put them together, right? So then I need to do this. I need to do y double prime plus y prime is equal to t squared e to the t. Okay, so y double prime oh, I see. You're going to do it by orders of e to the t, I think. Right? Okay. I think I see why Breskles is doing it this way. Right? This is v prime. This is v. Okay. So that's going to be equal to... So if we were to do this, I would get 2a e to the t v prime plus e to the t v plus e to the t v prime. Okay. And then that's going to be plus the first derivative, which is v prime e to the t plus v e to the t. And then this is all equal to t squared e to the t. Okay, beautiful, actually. You are right, Breskles. These all go away. All the e to the t's, we're just going to cancel out. Beautiful. Okay, so then I'm left with 2a plus v prime plus v plus v prime plus v prime plus v is equal to t squared, right? Okay, so that's 1, 2, 3. So we got 2a plus 3v prime plus 2v is equal to t squared. And remember, v prime was equal to 2at plus b. So that's going to be 2a plus 6at plus 3b plus 2at squared plus 2bt plus 2c is equal to t squared. Okay, then let's order by powers of t, right? Because this is plus 0t plus 0. Same as partial fractions. This is very, very cool to me that this works out the same way. All right, what do I got with t squared in it? I got this, and that's it. Cool. Okay, right, and this is going to be 1t squared. So that tells me that 2a is equal to 1. Then from this, in front of t, I got a 2b and a 6a. So I know that 6a plus 2b is equal to 0. And then for my constant term, I have this, this, and this. So now I have that 2a plus 3b plus 2c is equal to 0. Okay, some very cool stuff that comes from this, right? A is equal to 1/2. If a equals 1/2, that's 3. So that means b must be equal to negative 2/3. No, negative 3/2. Okay, and then if I put that into here... Okay, so then that's 1 minus 9/2 plus 2c. So... what is that? C is equal to 11/4? Is that what you got? Let's see. Well, you did a bunch of stuff here. Oh, Jesus, what's happening over here? What? Bruh. Dude, what? No, why is there so much going on? Is this because it's the second method? Oh, I passed it? Where did I pass it? 7/4. What did I mess up here? Oh yeah, 2 minus 9 is negative 7. Right, so then you put it over, this is 7. Yeah. Okay. There you go. Okay. A is 1/2, B is negative 3/2, C is 7/4. Great. Okay. So that tells me that... Okay, so... y particular is equal to 1/2 t squared minus 3/2 t plus 7/4. Okay. Now are we done? Well, now you say y. Now find yh. I thought I did yh already. No. Oh, this is a different question. Okay, great. Okay. Okay, I was like, why is sine and cosine coming up here? Okay. And then YH was equal to this. I don't know why my handwriting was going up. But, okay. Cool. Yes, I forgot to multiply by e to the t. Yep, got you.
You're not that guy, Sal. Trust me. You're not that guy.
Damn it!
Yeah, there you go. So, y general is equal to c1 plus c2 e to the negative t plus 1/2 t squared minus 3/2 t plus 7/4. e to the t. Super cool. Okay, cool. That's actually not too bad. Albeit, I guess it is a little bit of guessing. The other way you could have done it with... Uh-huh. Very good. Paul's math notes. We fucking love Paul. Oh, you're going to assume it from the same table. Oh, interesting. Wait. So you still have to make the same assumption? Is there not a way to solve this without looking at the table for what that forcing function is? It's kind of rude. Okay, I see. This reduction of order technique is funny. So wait, you're reducing the order and then you're using integrating factors? Is that what you're doing? I feel like this is integrating factors. Yeah, okay, cool. Integrating factors, does that only work on first order differential equations? Yeah, first order. Okay, cool. Uh-huh. Cool. And then Laplace transforms. Okay. Cool. Yeah, that was not too bad. I wonder if there's a way to do that without guessing what the solution is. That to me is kind of like whack. Or are you saying I could have done it with variation of parameters? Did you... Sorry, I don't think you did variation of parameters, no? Right, this is the undetermined coefficients way. This is just the way that we did it. Okay. So wait, let's see if I can do it with the other one then. Let's see if I can figure it out. Where was it? Oh, it's over here. I would think on a diffie-q test, I guess you just have to like kind of memorize that table. Oh, you did the second one with variation of parameters. Got you. All right, let me see. Let me see what you did for the second one. Just real quick. Okay. So yeah, you calculated the homogeneous solution, you did the Wronskian, and then you do the integral, and then you're done. Yeah. Okay. Does the other one not? Let me try doing it with undetermined coefficients. So let me see. Okay. So let's find y homogeneous. So I'm going to say that y double prime plus 4y is equal to 0. So by the same token, that's going to be r squared plus r is equal to 0. Or r squared plus 4r, sorry. So r times r plus 4 is equal to 0. Right? So then y homogeneous is just equal to C1 plus e to the negative 4t. Great. All right, let's look at your table, though, for this sine garbage. Yeah, let's see. Let's see how much it's going to suck. All right, if my form is something sine t, I think that's just this. No? So I'm going to say, y particular is equal to a, right, because what was it equal to? It was equal to sine 2t. Or 8 sine 2t. I don't think I need the 8, right? The 8 I think will get absorbed in the a and the b anyways. So I'm going to say a cosine of 2t plus b sine of 2t. Great. Let's go find the first derivative. This is chill, no? What was that? Derivative of cosine is negative sine, right? So negative 2a sine 2t. And then plus 2b cosine of 2t. So then y double prime is just going to be negative 4a cosine of 2t. And then plus 4b, or minus 4b, sorry. Sine of 2t. Cool. Alright, let's plug it in. Let's do it to this. Alright, y double prime. Be all that. Then we're going to say plus all this. Oh, I see why this might suck. Am I going to say it's like 8 sine t plus like 0 cosine t? Cosine 2t? Is that an appropriate way to do it for undetermined coefficients? I don't really know. Oh, yeah, sorry. Right, yeah, it's not plus y prime. Sorry, it's plus 4y. Technically 4y. Okay. Is this legal, though? You know, usually when we're doing undetermined coefficients, it's like t squared plus t plus whatever, like c. Since I know I have sine and cosine terms, do you think I can do it this way? I see it is like the analogous thing. I guess I could break it up into Euler shit if I really wanted to.
You done messed up, Aaron!
That would just take a while. But okay. So minus 4a cosine t plus 4a cosine 2t. Oh, that's 0. That doesn't really help me out. And minus 4b sine 2t plus 4b sine 2t is also 0. Bruh. It all cancels. Oh, no, no. All cancels. Oh, man. Okay. Why is that, by the way? Which makes sense given that the homogeneous sine is of the same form. Yeah. Yo, what's up, Obi? Shout out to Obi, dude. Doing some differential equations, Obi. Your specialty, right? You love this stuff. Diffie Q, man. I was trying to do... So we had an earlier question. You're writing chem today, Jahan? Oh, wow. I like chem. I think chem's actually quite great. I like chem. This one we did, and we were able to use, I guess, undetermined coefficients and, like, whatever, this forcing term to get a nice answer. Oh, you're on PDEs. That's right. That's right. I knew you did some sort of differential equations. You do the Giga Chad differential equations. Yeah, partial differential equations. But you've taught ODEs as well. Okay, cool. All right, so yeah, Breskles is saying that because y double prime plus, I guess it's 4y, right, is the homogeneous solution, and the sign to that is c1x plus c2 cosine x is equal to 0. Undetermined coefficients is going to give issues. You seem cool, but I'm going to go study. Okay. Thanks. I appreciate that I seem cool. If you need help with your chemistry, by the way, I tutor chemistry as well. Feel free to come on by, and if you want to submit a question to our stream, we help out students live here. Here's the how you do it. Okie dokes. Alright, so this doesn't work. We can't do undetermined coefficients. Let me ask, like, what ChatGPT says. I'm actually kind of curious. I want to see why chat thinks this doesn't work. What was it? 8 sine 2t. Alright. Obi says, if your homogeneous solution matches your inhomogeneous part, you need to accelerate the inhomogeneous term to t times h. Oh. Oh, okay, this is also similar to partial fractions, right? You just, like, add another, like, times t. Right, okay, so a cosine 2t plus b sine 2t is already a part of the homogeneous solution. Oh, wait, I screwed this up, totally. Wait. Sorry, I thought this was y double prime plus y. Okay, I messed that up. Sorry, I was basing on this one. Sorry. Yeah, no, wait. This one is just r squared plus 4 is equal to 0. Oh, okay. Okay, you guys gotta catch me on that. What? Dude, what? Come on, guys. Okay. R squared is equal to -4. R equals plus or minus 2i. Exactly. Okay. This I know would be y is equal to, like, c1 e to the 2i plus c2 e to the -2i. But anytime you have plus or minus, like, whatever, e to the 2i, that type of shit, you can just call this c1 sine of 2t plus c2 cosine of 2t. Right, this is from Euler's equation. We all need excuses. I was putting food in the oven. Yeah. What, you saying you need to eat? Breskles, you saying you need to eat, dude? What? Okay, I get that. Okay. Because this is literally, yes, the same form as this, I can be like, this is kind of like an, oh shit. Oh shit. This looks like y homogeneous. Issues. Okay, so here's my question. Obi says if your homogeneous parts matches, you need to accelerate the inhomogeneous term to t times h. Okay, so I'm going to take my homogeneous solution and multiply this by t. Is that what we're saying? Very cool, Obi. Let's see if that works. And I get this. This is the same thing. For instance, if you're doing partial fractions and you have like 1 over x minus 3 cubed, right? This becomes a over x minus 3 plus like b over x minus 3 squared plus like c over x minus 3 to the third. This is kind of how I think of, like, you have to like boost it up. I know you do the same thing also in diffie-q. It's cool how math has like similar themes and things. Pretty fucking rad. Now you get a product rule for the derivatives. You're welcome. Yep, I do. You're right, I do. Okay, so this is about to get messy. So this is going to become a times t cosine 2t plus b times t sine of 2t. Okay. We just need to get to the second derivative. And actually, we don't even need the first derivative in our final thing. So, okay. Let's get yp prime. All right, so that's going to be a times derivative of the first thing, which is 1, times the second. So that's going to be cosine 2t plus the first thing times the derivative of the second. So I'm going to say plus 2t because then that's a chain rule. Oh, sorry. Minus 2t sine of 2t. Yeah? I think I got the first one right. And then plus b, same shit. We're just going to have sine of 2t. Then this is going to be plus 2t cosine of 2t. Okay. Now let's go one step deeper. Go one deeper. All right. Derivative of cosine 2t is just going to be negative 2 sine of 2t. This is another product rule. So this is going to be minus 2 sine of 2t. And then minus 4t cosine of 2t. Okay. And then plus b. This is just going to be 2 cosine of 2t. Okay. And then plus 2 cosine of 2t minus 4t sine of 2t. Okay, cool. Okay. Now, what was it? Y double prime. So we gotta do this one. All right, so y double prime was this hot mess. Okay. So this plus 4 times this is all equal to 8 sine 2t. Now, I think this is going to be 0 t sine 2t plus 0 t cosine 2t, right? Plus 8 sine 2t plus 0 cosine 2t. Is that the correct way to match up the undetermined coefficients? I'm ordering them by like what power of t is getting multiplied, and also whether it's a sine and a cosine. So I think that's where this is coming from. I wonder if I'm allowed to do this. I'm gonna get the power of Zach.
Bing bang.
By mathematical authority, it is bequeathed upon you that you may break up the dr dt.
Okay, separate by function first, then separate by powers. I think I did that though, right? Right, this is separating by function. And then I also separated by power of t in front, yeah? I don't think there's any t squared. Okay. So let's see where we have a t sine 2t. Put the signs together. Oh, you want me to put these two together? And then put these two together? Let me see. Easier to factor. Yeah, let's see. Let me see. I think I have a method for this. So I'm gonna look at like sine 2t stuff. So that's here. Or I'm looking for t sine 2t stuff. T sine 2t stuff shows up here and here. Right? So that's gonna be minus 4b, right? B times minus 4. Plus, oh shit, right, plus 4b is equal to 0. Well, duh. That doesn't really tell me anything new, does it? Okay. Let's look at t cosine 2t stuff. So, that and that, I think we get the same shit, right? This is minus 4a plus 4a. Alright, I'm not holding out much hope right now, guys. Okay, maybe for the cosine 2t. So we got here and here. So that's gonna be, oh okay, that one actually looks okay. So I'm gonna say 2b plus 2b, so 4b. So 4b is equal to 0. And then for the final one, the 8 sine 2t. I'm just going to have here, right? These are the only ones that are left. You're enveloping some tacos right now? Nice, dude. Okay. Yeah, so that gets me minus 4a, and that's equal to 8. So a is equal to negative 2. And b is equal to 0. Okay. So y particular, what do we say what y particular was? At cosine 2t. Okay. Is equal to negative 2t cosine 2t. And y homogeneous was equal to c1 sine 2t plus c2 cosine 2t. So I think our total solution, or general, right? It's just going to be this. And then minus 2t cosine 2t. Is that what you got? Yeah, c1 cosine 2t plus c2 sine 2t minus 2t cosine 2t. Yes, we did it. Good job, everybody.
That's dope.
Very cool.
Well done. Well done.
Nice. That's a fun one. Thanks, Obi, for... Yeah, I think I've seen that before. If you're, what is it? If your particular solution contains the homogeneous solution, then you need to bump it up. Bump that shit, dude, right? Yes, if I prefer that, yes. C2 minus 2t cosine 2t, yeah. That's another nice way to write it. Cool. You know, I'm going to save these for David. I'm gonna tag him saying we did it here. So one sec. Let me put this up on my own little website. Say, not David, or David later. And I think I can just paste this in there. Oh, can I not just paste? That's where I could have. If I take this, I should just be able to... Can I not paste? There it goes. Nice. Uploading. Nice. There's David later. Cool. And then I'm going to mark that one as the one we're doing. I'm going to mark it as done. Did you ever do tensor calculus? As a separate course, no. I definitely encountered them in grad school. I definitely encountered tensors. But I'll be real with you, like, they scare me.
Oh, no.
Especially when if you ask someone to define a tensor, they say, oh, it's something that looks like and behaves like a tensor. I'm like, excuse me?
Oh, no.
Can't say that. Why is that coming up? Be right back. I did not put that in. Chill. There we go. Very cool though. So one way I guess is to use that table for if the solution looks like this, then particular solution, sorry, if the whatever's on the equal sign looks like this, then the particular solution probably looks like this. Yeah, this thing is super handy. I don't think it's too bad to memorize, right? Constant, linear, quadratic, cubic, those all make sense to me. If you have a sine or cosine, it has to be cosine and sine. E to the x is e to the x, and then if you multiply them, right? So a linear times e to the x is the linear particular times e to the x. A quadratic is the quadratic times e to the x. If you multiply by sine, then you got to do the thing times all the sine. Yeah, this is so cool. I really appreciate this. Thanks for showing this to me, Breasticles. And then this is interesting. If you have a quadratic times sine, then you have two separate quadratics for the cosine and for the sine. I guess that makes sense, right? Because the cosine and the sine coefficients are the same, or different, sorry. I was working through Pavel Grinfeld's book and got stuck at chapter 3 for years. Partly why I'm working on PDEs, just get used to playing with the subscripts. Yeah, so, I mean, tensor calculus, correct me if I'm wrong. Is that the stuff where we see this? Where it's like T, U, V, and then like G, like V, U or something. And then like these like cancel each other out or something. They do it a lot in like, my friend who does quantum gravity does a lot of it. Yeah, sub and superscripts, yeah. You can use the same method for systems of ODEs too, and the algebra is utter hell.
Oh, no.
See, that's why we have AI. That's why we have AI. AI can go ahead and just do all the algebra for us. Yeah. That's cool. I will eventually, in my life, Obi, get up to doing PDEs and things. I never took PDEs. DiffyQ is the highest math, I would think. I take that back. I took complex analysis. I think complex analysis is a little bit higher than DiffEq, right? In terms of like difficulty. Complex analysis has a lot of really like cute tricks for integrating things in the complex plane. Yeah, okay. Yeah, it was Calc 1. Actually, I take this back. I got AP credit for Calc 1 and Calc 2, so I didn't have to take those in college. So I went straight into vector calculus, which I think is Calc 3, really. And then from that, I want to say I took DiffEq next. And then I took linear algebra. Linear algebra was like kind of chill. And then after linear algebra, I think I took complex analysis. And then I stopped. I didn't go up to real analysis. I didn't go up to, what's that other one? Everyone always gets discrete. I never took discrete. Is that a hell of a jump? Yeah, I don't know. I guess it was just the progression we had. But yeah, I never took discrete. I never took real analysis. And then I never took PDEs. Most people take real before complex. Yeah, for whatever reason at UT, real analysis was seen as harder than complex analysis. I think from the physicist point of view, I think we use a lot more complex analysis to solve like weird integrals than we do real analysis. So I think I understand why. Oh, you don't take real analysis till grad school? Yeah, no, we had it for undergrads. I mean, it was upper division for sure, but yeah, discrete to me is, man, it's just all like the rules and the proofs and like it's very jargon heavy. I remember from my friends that would take it, they would say it's not so bad. They're like, oh, discrete isn't that hard. It's not that hard. But me just glancing at it, I'm like, this isn't math anymore. This isn't, there's no more numbers. Oh, interesting. Senior and grad level. Well, I mean, I'll be honest. I don't think my complex analysis undergrad course went into probably the same extent that a grad level complex analysis course went. We did like, integration around poles and things, but anyways. Cool. Another raid from Dawn. What's up, Dawn? The Dawn father, dude. It's Dawn. Dawn factorial. Dawn, you like this? We were doing some pretty chill differential equations just now. We were talking about the different math courses that people take in undergrad versus grad. So I think there's kind of a consensus here that real analysis is sometimes a graduate course. But I feel like, Dawn, you've done real analysis. Did you do it in undergrad? I know Dawn's also in a graduate program. I think he's getting a master's in, I forget if it's applied math or just math. Hell yeah, DiffEqs.
That's dope.
You know what's up, dude. Hell yeah.
My name is Jeff.
Where's Jeff? I'm calling for Jeff. Pennet says, I've taken Calc 1 to Intro to DiffEq now. Calc 3 next. So, yeah, that's interesting you took DiffEq before Calc 3. I think you want to do like Calc 1, 2, 3, just bang them out. DiffEq is by far the hardest. I enjoy DiffEq. I think DiffEq is one of the funnest. It is kind of one of the most annoying ones because a lot of it, as Bresticles was pointing out, a lot of DiffEq is just conveniently guessing and checking to see whether your solution works or not. But the techniques I think are super cool. Integrating factors is like so fun to me. It's like it's a reverse product rule. You're like, whoa. Don says, I had the option to do real analysis in my undergrad, but I dodged it. Yeah, good.
Yeah.
I would have dodged it too, honestly. I think of it as like a second or third year undergrad course for the introduction to real analysis. Oh, you just graduated, dude. Congrats, dude.
My name is Jeff.
Come on, Jeff. Say congrats to Don for us. That's dope.
That's dope.
Congrats on finishing grad school. It's a fucking journey, I'll tell you that. I'm sure you're sick of hearing this, but this is what every person will just like hound you after you graduate. They'll say like, "Hey, what's next?" Like, what do you have planned after this? And I'd always be like, I have no fucking plan. I just like staying in grad school. But yeah, if you do have a plan, yeah, let us know. I'm curious. I'm always curious to see the trajectories and also like show my audience, like, some people, they don't want to go into certain programs or certain fields or certain, you know, programs, graduate stuff, because they feel like they get pigeonholed into, I have to become a professor or I have to do research. And I'm like, no, dude. Like, you know, some of my friends who went to grad school make millions of dollars like developing, I don't know, like chemicals right now. Like, they'll do like things that are not related to their PhDs. Taking a fucking break. Hell yeah, dude. Yeah, exactly. Yeah. What's up, Hacker? Yeah, being a student would be nice. Yeah, just the nice thing about being a student is no one really asks like what you're doing. You just say like, "Oh, I'm working on my PhD." And they're like, "Yeah, cool, great." It dodges like the accountability question of, well, you know, have you gotten married yet? Are you buying a house? You know, do you have kids? And you're just like, "No, I'm just in a PhD program." They're like, "Oh, yeah, okay. Yeah, work on your PhD. Totally fine. Yeah, you don't need a career. Just work on your PhD." But yeah, you're applying to data-related jobs. Smart, especially in Seattle, right? That's my sister. I think I told you, is a pediatrician at, I forget which medical thing in Seattle, but apparently it's pretty well known for, maybe it's Seattle Medical Center. It's kind of northish, maybe. But she tells me that she's always going on like, I don't know, like random speed dating things and whatnot. She says everyone here is just a data nerd. I'm like, yeah.
My man.
Seattle, dude. It's like tech data center. Right? Microsoft is down the street or something, right? But the dream job would be bioinformatics, which is data analysis for medical research. Sick. That's very cool. Yeah. I like Seattle too. It's pretty cool. I had a good time when I visited briefly for family. I also had like a 6-hour layover that I went into, what is it, the market and stuff. Next time I'm in Seattle for like a longer period of time, we're gonna meet up. I promise. I totally blanked the first time when I was there in January for like a post-Christmas reunion with my family, and after I got back, everyone's like, "Wait, Dawn's in Seattle." I was like, "Oh,
no,
I fucked up." I should have said hi. Right, perfect amount. Yeah, it was a layover from Japan too, actually. So I was like super jet lagged. I got off the plane and my sister picked me up at the airport, SeaTac or whatever, and she was like, "All right, you wanna go get sandwiches?" And I'm just like barely staying awake. But yeah. Ethan says, "Hey, Dr. Gold, I was lurking, but I see there's no voice chat." Yeah, that's just because technically these are office hours for like my UCLA kids, and I have to like kind of regulate what gets said on the voice chat. But after this week, Ethan, we're gonna go back to normal streaming, and yeah, I'll have the Discord open. You guys can talk and say whatever. It's just, yeah, I have a job I have to like make sure I don't get fired from. But yeah, let me see. How long was my PhD? 9 years. It shouldn't have been that long. It was just because my project got switched halfway through. There was COVID. Honestly, I also I didn't really feel a need to graduate because I was just living the dream. I was just doing physics experiments, getting paid, yeah, minimal amounts, but also it's kind of nice. You're just avoiding any pressure from society to like go become an adult. I say like grad school is like college forever. If you really like college, just go to grad school. You can just stay in college forever. But eventually, yeah, my advisor was like, "Okay, 9 years, you gotta leave." I was like, "Okay, cool." Well, let's see. Grad school's my PDE teacher would always ask, "What's next?" because everyone else was a senior and he always forgot I was a sophomore. Yeah, what's next, Breasticles? What's up, Jack? What's going on?
Hello.
Dun, 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 dun.
I was stopping by to ask, so I wasn't able to make today's lecture. Were there like
Okay.
any super like important announcements that you did not get recorded? Because I'll go check on that one later.
Oh no, all the lectures are recorded. So yeah, if you just check it, I don't think there's anything. I mean, there's the importance of we have a final on Friday. I guess that's what I'm really like trying to make people understand is that they need to show up to the final on Friday.
Okay. Besides that, so today was the last day for our last homework stuff.
Yes.
Just double checking. So in the past, I wasn't able to answer all the questions correctly, and I just had put some answers there. So
For what? Sorry.
What?
Sorry. Repeat what you're saying again. Sorry. Something about answers correctly paper.
So basically on the homework, some of the questions I just got wrong. I wasn't able to guess them in the 2 attempts or whatever.
Okay.
So I mean that's points off, right?
Yeah, it's minimal, right? Your homework isn't worth that much.
Oh, okay.
Wow.
Because on a few of them at the when I was running out of time, I just put a random number on there because at least it's that I completed
What?
it.
No. Just put a random number. I mean, I guess it's better than nothing, yeah.
Well, I was confused because this is a while back when the earlier weeks, and it was having that weird kudu glitch.
Yes, when that was having problem. Well, that's why for the first 2 weeks, we're just gonna exempt all the homework. I'm just gonna give full credit for the first 4 homeworks because
Okay.
nothing was submitting correctly. I was like, yeah, fuck this, dude.
Oh my god, bro. Oh, hell no, man. What the fuck, man? Get your ass on.
Anyways.
Okay. So if we made some attempts, we get some partial credit. If you obviously got it right in the 2 attempts, you get full credit. But if you didn't answer at all, it's just all the credits gone then.
Yeah, but I think it's only one point. Usually there's 24 questions on the homework.
Yeah.
So yeah, if you couldn't figure it out in 2 attempts, I mean, because those are multiple choice, right? The 2 attempts is because there's 4 choices.
Yeah, and there were also a few of the math ones where I thought my numbers were off a little bit, so I just put a slightly different answer in.
Yeah.
So 1 or 2 of those in the past I got wrong. So I guess would that be 0 points still? If you don't get it right, you lose all your points.
That's the current grading scheme, yeah.
Damn.
This is also, I don't know if I said this, but I tell students try to do it on your own for most of the attempts, and then when you're on your absolute last attempt, I don't really care if you go to AI and just plug it in. But
yeah. Well, some of these had diagrams, so obviously you can't throw a diagram in there.
I don't know. AI is pretty fucking good with diagrams these days. It can get almost everything correctly.
How do you even throw a diagram into an AI?
You just copy paste it. Just take a screenshot.
Oh.
I feel like I shouldn't be teaching you these things though, because it becomes a temptation. Kids are just oh, I can just feed the whole thing in and just get the answers. And I'm like, no, you need to actually do the work.
Okay. Then you finished writing the exam for Friday, right?
No, I haven't finished it yet.
Okay.
I still gotta transfer all your grades over tonight. Yeah, I was waiting for the last assignment to be due, which was the homework, which was due at 2. So now that deadline has passed, well, first I'm gonna go to the gym because I need to exercise. But after I get back from the gym, I'm gonna start transferring everything over, and that takes forever. No. Yeah.
Okay. Let's see. I mean, I know you said you haven't finished writing it, but if you had to put a percentile, obviously 50% is going to be stuff we've done the last 2 weeks.
Yes.
But are you then going to try to spread that remaining 50 percentile evenly over the remaining, I guess, 8 chapters? Would that be 8? Yeah.
Yeah. I think I'll do one of the FRQs will be things we've learned after midterm 2.
Okay.
One of the FRQs will be from basically midterm 1, or a similar topic to midterm 1, and then the other FRQ will be from midterm 2. So I think how I have it structured, I'm going to do 3 FRQs at least, and I'll split it up as first midterm, second midterm, everything from second midterm to now. And then amongst like the multiple choice and stuff, it's kind of the same. I would say like it's a third, a third, a third. Maybe not half, quarter. Maybe a third, a third, a third. But again, like what's the difference? It's like a question or two, maybe.
Okay. So, okay, if it's 3 FRQs, I'm just trying to think how much time I should take on each question.
Oh, yeah.
3
Well,
FRQs.
you get
each
6
with 3
hours.
parts. So like
You get, yeah.
9 questions for the FRQ.
You shouldn't be taking an hour per FRQ. It should take like maybe like 20-30 minutes. Maybe. I think you can easily get the exam done in 3. I extend it out to 6 just in case someone has technical errors and like the internet dies, or I don't know, like their cat has diarrhea again or something.
Oh no.
I've had so many funny emails and excuses. Although I will say you guys have been pretty decent. The last time I taught this class, someone asked me to move the exam because it was their birthday. They said, "Can I take the exam later because the exam's on my birthday?" I'm like, what? Excuse me?
Oh no.
Dude, what? Oh man. But yeah, definitely go through the lesson, Jack, because the types of questions we went over today during lecture is very similar to what will be on the final.
Okay. In that case, I have some questions for homework 10.
Let's do it. What do you want?
Okay. So let's see. First one. Where is it? Give me a sec. Number 4.
Okay. All right. 10, number 4. Ooh, the circuit. Yes. Yeah, you know, this is a good one. Zanira actually asked about this question too. I'm gonna mark this as Zanira's. Let's learn about circuits. Alright, let's see. Alright, consider the circuit shown below. What is the current through resistor 1? Alright. What's your this is we kinda did this one during lecture, but what's your general process?
I saw this one was what you did in lecture.
Uh-huh.
So just so I understand the process correctly, before you start, you want to like go and like draw the direction of the currents.
Good. Yes, you want to label some currents, right?
Yeah. Then you also want to like, once you see the direction of the currents, you kind of want to like figure out if it's going clockwise or counterclockwise inside a loop.
So you don't need to figure out if it is exactly, you just need to pick a convention. You're not determining the directions of anything, although it kind of helps to try to guess them, I guess. So, yeah. And if we get negative numbers for the currents, that means that our guess was wrong. That's all that really happens here. Okay, so, for instance...
I thought a negative current was like, it's in the opposite direction of whatever the current you said it was, right?
Yes, exactly. That's correct.
Okay.
Okay. So I'm going to call everything through here, for instance, I2, and I'm picking like this direction for I2. And then I'm going to call any current in this loop, for instance, or not loop, right? It's kind of like I call it like juncture. I'm going to call this like I3. Because then the key thing here is this is a separate current.
Yeah.
And this one is, I'm going to call this I1. So currents become separate, and anytime you have like meeting points, they have to have different current. Because this, and this are all in series, right? Things in series all have the same current. That's why I can call this I2, I can call this I2, I can call this I2.
Okay. So junctions, are they where like two different currents meet?
Good, yes. When wires meet, right? So when wires meet, or like branch off or spread or whatever, that's almost always going to be the time for you to label a new current.
Well, I thought you could put a junction between a resistor and another resistor if they're in series. Can you not do that?
No.
Oh, then
No. So you're saying if I had this, for instance, like this?
Yeah.
Yeah.
Because aren't you? I thought a junction was put someplace where you have a voltage change or something like that.
No, junctures are where you have currents changing. So, for instance, these two resistors, these are in series. So whatever the current is here is the same as the current here. So a juncture wouldn't make any sense. The current's not splitting off anywhere. If, however, I don't know, let's say, for instance, we had like this. Now these are different currents, right? Now this is, for instance, I1, this is I2, and then this is I3. Because the currents of things in parallel aren't the same. The total current here does equal the same as the total current here, and you should see that from Kirchhoff's juncture law. Do you see how, for instance, current going in, I1, is equal to the current coming out, I2 plus I3?
Yeah, so you would have a junction between where you have that black dot, and then you have another junction where I2 and I3 meet, right?
Yes. And this should make sense, right? Because this I1 here.
So it's where current changes, right?
Correct. But current changes whenever current splits. So whenever current splits into different paths, that's where you got to start labeling new currents.
All right.
Okay. Okay. Cool. Okay, so once we got this, we're going to do some loops, right? And this is where I need to pick a direction for my loop. I'm going to call this, clockwise. I'm going to call that loop A. And I'm going to call this loop, which is counterclockwise, loop B. So then let's write out loop A's KVL laws, right? So if I start here, I go across V1, so that's V1. I don't really care about I2 with batteries. I don't really care about I2 with no wire here. But then I'm going to come across this. And notice the direction I'm coming across is the same direction as the current I was saying it was going in. And so for resistors, that's a minus. That's a voltage drop. And so that's going to be minus I1 R1. Then we come around here. Now we're going across R2 with current 2. And we're going in the same direction. So that's going to be minus I2 R2. And then this is all equal to 0.
Okay. Yeah. Okay, I get that part.
What about loop B? What would loop B be?
Loop B, it would be V2 minus I1, or not I1, I3 R3.
So V2 minus I1 R1. Right, and then minus I3 R3. Yeah. Cool. All right, I have 3 unknowns here, right? I1, I2, and I3, which means I need 3 linearly independent equations. So I need 3 equations. Where can I get my third equation from?
So wait, hold on. Why do we need to find a third equation?
Because we have 3 unknowns. I don't know I1, I don't know I2, I don't know I3. In a systems of equations, the amount of variables you don't have, or they call them free variables or whatever, you need at least that number of equations. And they have to be linearly independent too. So there's actually kind of a funny thing here. If you were to, for instance, build, let's say, another loop, because this will happen sometimes, students will be like, oh, let me do this loop. Let me go all the way around, right? Let's call that loop C, for instance. Watch what happens in terms of the equation. That's going to be V1. And then we're coming across V2, but we're going the opposite direction across the battery. So that's going to be minus V2. And then now as we come this way, do you see how we're going the opposite direction across R3? Yeah, what's up, JC? So this is going to become plus I3, R3. But then we're going the correct direction across R2. So that's minus I2, R2. This is equal to 0.
Okay, so originally it's what's it called? The Kirchhoff's voltage equation. It's like the sum of like the voltage changes has to equal 0, right?
Yes. Yes.
So that's why when everything like IR1 and R1 and like I2 and R2, they're actually positive. You just move them over to the left hand side. That's why I3 R3 is positive, because it was originally negative.
Well, no, not quite. Not quite. Okay. So in Kirchhoff, if I'm saying the direction of my current is this way, but the path I'm taking is this way. Let's say this is the path, and let's say this is R1. Oh, I see. Oh, you're saying the sum of the voltages has to be equal to... Wait. Now, Kirchhoff says that the sum of the voltages has to be equal to 0, right? This is what KVL says inherently. So if I travel...
Is it the sum of the voltage has to equal 0, or the sum of the voltage changes?
Well, going across a battery is still a voltage change.
So, okay, so if like... Oh, so are you saying like at the positive terminal, there has to be like 12 volts, but at the negative terminal, there's 0 volts. So
yes.
But for whenever you go through the whole battery, you have to make sure to get to 0 volts.
Well, you have to get the whole thing about KVL is you have to get back to your starting position. What it says is that my potential where I start and where I finish is the same thing if my start and finish are the same thing, the same place. If I start here, right, then whatever path I take, if I come back, I need to be at the same voltage. So we assume that the starting voltage is 0. Okay? And then as I go across this, right, if this is a battery, let's say, for instance, this is 1.6 volts, right? So this is 1.6. This is 0. So technically going across this, I'm gaining voltage, right? Coming from here to here is a positive 1.6 volts.
Yeah.
If there was a resistor right here, right? This end would still be at 1.6 volts, but this end would be lower. This would be at like, I don't know, like 1.2 or something.
Yeah, because over time, your voltage is decreasing.
No, not over time. Across a resistor, your voltage is decreasing.
Over a resistor, so a resistor, as the current goes through it, it's going to combine and it's going to
here's the other key thing. So current, right? Current moves from high voltage to low voltage. If I've defined my current moving this way, that means this is the positive or the higher potential, and then this is the lower potential. So my change in potential going across it is negative. That's why we get negative I1 R1.
So it's negative because it's going from high potential to low potential.
Yes.
So that's a I guess a decrease.
Decrease in potential. Yeah.
In electric potential. Okay. Then I3 whenever you go through it.
So when we go across this one, right? I've defined current to be this way, such that this is the low and this is the high. So if I'm taking my green loop and I'm coming around this way, notice I'm coming in the opposite direction that I've defined the current. So the change in potential is positive because I'm going from lower potential to higher potential. And that's why on the green one, this is a plus I3 R3.
Okay, so by going the opposite direction of the current, you're traveling from low potential to high potential. That's why it's positive. But when you're going from the normal path of the current or following the path of the current, it's positive to negative, or a higher to lower potential. And by going higher to lower potential, that is a electric potential decrease.
Yeah.
So that's why it's negative. Okay, then obviously, when you go back to look at your battery, you have a positive terminal and a negative terminal.
Mm-hmm.
Positive terminal is where you have the highest
potential. Yeah.
highest electric potential. And you want to make sure to get to 0 electric potential
When you return
when you turn
to your
the
same
negative
position.
terminal.
Yes.
So wait, is Kirchhoff's law saying your start wherever you start in terms, so the electric potential at where you start
Mm-hmm.
has to be equal when you come back to it?
Yes.
Okay, hold on, give me a sec.
If you end up taking like double E courses, sometimes your start and your finish won't be the same place, but you'll know what the potential difference is between those two places, and you can use that to still like help you figure out what the other components are. Right? So sum of voltages has to equal the change in potential, and if it's the same start and finish position, then delta V is equal to 0. Right?
Okay, Kirchhoff's law isn't talking about voltage. I thought it was talking about. Oh, wait, hold on.
No, it is talking about voltage, for sure.
Well, is it saying that electric potential at your starting point, or oh wait,
Electric potential is voltage.
yeah, I know, but electric potential. Well, voltage is electric potential difference.
Correct. Okay, yes. It's always referenced to something. Yeah.
Yeah. So, is Kirchhoff saying that your starting point's electric potential is
Yeah.
0?
If you assume it to be 0, then when you get back to it, it has to also be 0.
Okay. So that means the voltage has to equal 0.
Reference to ground, yes. Correct.
Okay. Yeah.
You always have to reference something. Voltage always has to be referenced to something. In this case, yeah. Usually the ground is 0 volts, is what we say. The same way where like the potential out at infinity is assumed to be 0.
Okay, so that's why. So over the course of this circuit, the voltage that's coming out of the positive terminal of the battery, as it goes through a resistor, it's being multiplied by the resistor's resistance, or not resistance, but it's being, sorry, on anything.
It's okay. Yeah.
Over time, because the voltage is pushing out charge, which makes a current.
Good.
And whenever the current passes through a conductor, it makes power.
Yes.
And power is, power is equal to the change in energy over time.
Okay.
And the change in energy in this case is the change in electric energy.
Sure.
And obviously the electric energy originally goes back to whatever chemical processes are happening in the battery. So over time, as you're using energy in a resistor to make heat or light or something, it's taking away some of that potential energy that originally
from the battery. Yes.
From the battery. That originally held back from the battery.
Okay, yeah. In these equations, we assume the batteries have unlimited capacity, right? We're not worried that the voltage in the battery is going to drop.
Yeah, we're assuming the voltage is constant.
Yes, there you go.
Yeah, but over time, over time
the battery will drain.
Yeah, over time the battery does drain because you're just pulling more and more potential energy out of it.
Correct. Yeah, the energy has to go somewhere.
But then let's assume the battery's ideal. Then that our starting voltage as it goes through the circuit, it has to equal 0 when it gets to the negative terminal.
Yes.
Because you have to go from higher to lower potential, and you need to keep going to lower potential.
Sure,
right?
sure. Yeah. This potential, when I say this is 1.6 volts on a battery, that's the difference between this terminal and this terminal. In reality, this could be like 3.2 and 1.6. If, again, I'm measuring this referenced to like something that's already at 1.6 volts.
Okay, but like let's just say screw it. That the negative terminal is 0 or
Sure,
whatever,
sure.
right?
Call the negative terminal 0. Yeah, it's all relative.
Everything's relative then. Okay. Then over the course of the circuit, the voltage is being consumed, right?
Yes, you're dropping voltage across resistors. You can also
Because as
gain
it goes over
voltage.
more resistance,
Yeah.
it decreases.
Uh-huh.
That's okay. That's what makes the current. Okay, that makes sense. So if you had a situation where, is that why whenever you have a situation where it's just a battery in a circuit by itself,
Mm-hmm.
that's why is that why it overheats so damn much?
Yeah,
It's like
this is bad.
the resistance is so low,
Yeah, this is bad.
that the current is so high and that there's so much charge pulsing through that battery that it's getting it
Right,
gets really hot.
if this is R and this is V, then by V equals IR, right? Do you see how I through this battery is equal to V over R?
Mhm.
And that should make sense, right? If this is plus 6 volts, anywhere along a wire, if there's nothing in between, this is also going to be at the same potential. And then this is at 0 volts, right? Because this we assumed was at 0 volts as well, right?
Yeah.
So this shows, right, how if I start here, I gain 6, I lose 6, I'm back at 0, right? But in terms of current that's going through, right, that's V over R. If this is very small, infinitesimally small, let's say it's like really, really close to 0, then I gets like huge. And that's how fires start. Because at the end of the day, right, power is equal to I times V. The voltage is set by the battery, in this case. So if this goes up to infinity, the power goes to infinity, and then you end up just like having a bad time. You'll create smoke monsters.
Okay, thank you very much.
Yeah, cool. All right. Do you still... Well, you still want to run through this though, right?
Yes.
Yes, okay, cool. All right. So, okay, good. I'm glad we got that straight. So, what I wanted to show you is that sometimes students will say, like, let me create a third loop that just goes around the whole thing. And so we came up with this equation. Because we started here. We went across V1. We came this way. We came the opposite way across the battery. You see how we went from the positive 1.4 to the 0? That's why it's a drop in V2. Does that make sense? Coming this way? Why we added V1 here, but we subtract V2 here.
Sorry, what?
So, coming across this battery, right, is plus V1. But then when I come across V2 here, this is minus V2. Do you understand why that is?
It's plus V1 because...
If we're starting
it
here and we're
is-
coming all the way around.
let me think. So wait, you're saying you're starting at V1, right?
We're starting below V1, yes.
Oh, you're starting below V1. Okay.
Yes.
And as you go from... If you go over the battery, you're going to get a positive electric potential difference.
Yeah.
So it's going to increase to have a positive electric potential difference. You're going to travel around till you get to the positive terminal on the second battery.
Yeah.
And then that's going to be like, if you go through there, then you're going to be going from the, let's see. That would be a negative.
Good.
Or that's going to be a decrease in electric potential.
Right. Which is why it's minus V2.
Minus V2.
Good. Okay, so then when you get to here, now you're coming across R3, but you're coming across the opposite direction that you said the current was. So that's why that's plus I3R3. Because if we define the current here, going in that direction, that means this is positive and this is negative. So in fact, I'm gaining voltage across this.
Okay.
And then when I come across I2, now I'm going in the same direction as I defined the current. So if I defined the current going this way, then this is positive, this is negative, this is a drop of voltage.
Yes, because going from lower potential to higher potential, that's an increase in electric potential, right?
Yes, good.
Okay.
Now, so we come up with this equation for our loop. What I wanted to show is this equation here, C, is the same thing as just doing A minus B. Notice if I do this whole thing minus this whole thing, see how I get V1 minus V2. I'm going to get minus I1 R1 minus I1 R1, so these are going to cancel. And then I'm going to get minus I2 R3 minus, which is plus I3 R3. So this third loop I came up with does not help me because it's just a combination of the other two.
Okay, so whenever we're like putting together systems of equations put into a matrix, we want to make sure that whatever variables inside them, they eventually can like. Okay.
They eventually can row reduce, yeah. Otherwise, you're gonna end up getting in like the matrix, you'll end up getting a row that's just zeros.
Okay.
If they're not
independent.
Yeah.
In
if
a
they're
matrix, are we only trying to solve for one unknown, or can we solve for more?
We're solving for all of them. We're doing it all at the same time.
Okay.
Yeah, you can't really solve for just one. I guess maybe you could. If you tried to like just reduce the bottom one, I guess. Yeah. But in general, you're just going to slam this into a calculator and tell it to row reduce. And then it'll just give you all of them.
Okay. Do you think we're probably going to see something like this on the
100%.
exam.
There is 100% going to be a circuit. And there will 100% be one that you need to like put in a calculator.
Okay, got it.
Okay. So from this, you get C is equal to A minus B. So C is not useful. So this is not, so this is like not useful. So instead, I want to use another equation. I'm going to use a juncture equation. Juncture equations are nice. So let's use this juncture. Let's call this like juncture D, I guess, right? And so from D, we know that like current in is equal to current out. So that tells me that I2 plus I3 is equal to I1. Right? So current coming into the juncture is equal to the sum of the currents coming out.
Okay, so that's why, so is I1, that's positive because it's going from low potential to high potential, right?
I1, not necessarily that we don't know if I1 is positive or negative. We just defined it as going in this direction. So relative to the juncture, it's moving away from the juncture. So it goes on one side of the equal sign. I don't know whether I1 is positive or negative.
So, okay, so how I was doing it was like whenever I would draw out my arrows for like what direction the current was, I would like, if it's going with the direction of the current, it's negative, but if it's going, not negative, sorry.
Sorry, you're saying if the current goes with the direction of the current. So wait, there are two currents?
If the current, let's say whenever I have like, say, where is it? Let me find it real quick. Wait, is that person? I made I1 positive because the direction of the currents of both loop 1 and 2, or I guess A and B in this instance, they were going both in the direction that I1 was pointing.
Yeah, you don't want to do that. You don't want to say that I1 is positive or negative just based off what these loops are, because that can change.
Okay. Then why did I? Oh, I see what I did. I said that I1 as it entered the junction was equal to I2 and I3
Okay,
as,
cool.
as I left. So it's I1 equals I2
So
plus
you did
I3.
this one. Yeah, you did this
Yeah.
one. Yeah.
Okay.
So
that's
I1 equaling I2 plus I3 is the same thing as I2 plus I3 equaling I1.
okay.
Yeah, don't think about positive and negative yet. Just for at least for the current, for the juncture laws, for the KCL. You want to think about, like, is it going into the meeting point or is it leaving the meeting point?
Okay.
Okay. So then the next thing I want to do is I want to arrange as a matrix. And how I want my matrix to look, think about what the unknown variables are, right? So the unknown variables are like something I1, something I2, something I3, and then we're going to go dash, 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 and we're going to say is equal to whatever's here. People in my chat will yell at me and say, wait a minute, like, mathematically this isn't right. It's supposed to be like I1, or what is it supposed to be? It's supposed to be like A, B, C or something. And then this is supposed to be I1, I2, I3. And then this is supposed to be like whatever, like the sum of the voltages. But don't worry about that. I'm not going to make you guys do linear algebra. So I want it to look like something I1, something I2, something I3 is equal to a number. So if I go and look at this one, right? I'm going to like put all these things over to the right. The I terms, right? So I'm going to say this is I1 R1 plus I2 R2 is equal to V1. Do you see how I just like took this term, moved it over? I just took this term and I moved it over.
Yes.
Okay. So that means this is R1, this is R2, and then this is 0. So then we're going to look at this one. This one was I1 R1 plus I3 R3 is equal to V2. So I'm going to say, okay, cool. So this is R1. There is no I2, so this is 0. And then there is an I3 here. So I'm going to put R3. And then this was all equal to V2. And then finally looking at this one, equation D, right? This is going to be negative I1 plus I2 plus I3 is equal to 0. So I'm going to do negative 1, 1, 1, 0. Because this is the same as negative 1I1 plus 1I1 plus 1I2 plus 1I3. And then we're going to say it's all equal to 0. Okay.
Okay.
So now let's like put in what our matrix is, right? So R1 was what? A kilo ohm? Sorry, no, wait. R1 was 2 kilo ohms. So I'm going to say like 2000. R2 was 1000. 0. Maxwell says, this could have helped me back in freshman year of engineering. I agree. Yeah, this is a very common thing in freshman engineering course. What's up, Maxie? Are you still in college? Let us know. Okay, and then this one is going to be multiple batteries. Yes. Do you have a screenshot of one with multiple batteries? I can show how multiple batteries work. Or like a specific type of question with multiple batteries. And then what is it? R3 is 1,000. And then V2 was equal to 1.4. Nice, senior. Congrats, dude. Okay. Then negative 1, 1, 1, 0. Okay. This is the matrix we set up, right?
Yeah.
All right, so then the last step is to RREF this. Nice. Maxi, do you know about like Thevenin, right? Thevenin circuits, Thevenin voltage. There are all these really cool electrical engineering hacks for doing even more complex circuits than these. But I think they're all technically based off of Kirchhoff's laws. They're just like, they're neat little tricks. Okay, this is going to be a 3x4. Ugh. Go cross. Excuse me. Hello? Excuse me? Oh, what? There we go. Mesh analysis. Yeah, mesh analysis is great. That's another one. Probably did stuff with like phasors too. Things get even crazier when you do like AC circuits. Then you got like impedance. There's a whole other world out there of this stuff.
Also,
I forget.
question.
What's
So
up? What's
whenever
up, Jack?
you're calculating the total power used up by like all the resistors in this circuit. On the lecture notes, you had power equals current times voltage, which I know doesn't make sense.
Why does it make sense?
Well, it was just power times. Sorry, it was current times voltage. That's it.
Yeah, that's power. Yeah.
Wait, isn't power I squared times R?
Correct. So power is equal to IV, but remember V is equal to IR.
Yes.
So technically, if I slam this in for here, it's also equal to I squared R. This is the easier. This is the easier equation, of course, to solve for power because you already have the R's and we're literally getting the currents here.
Yeah, no, what I'm saying is in the lecture, it's just I times V.
Yeah, that's fine. That's also correct.
But you're not squaring the current.
You don't. Yeah. I times V is the same thing as I squared times R because V is equal to IR.
Yeah, no, but sorry, in the lecture, it's just I times voltage. No,
Yeah,
sorry, not I times voltage, sorry. Let me double check. I think it's just I times R.
Yeah, that's wrong. Power is not I times R. Power is I squared R.
Yeah, hold on, let me double check.
It's okay. I make mistakes too.
Yeah, it just says I times R.
Okay, well that's wrong.
Okay, I thought it was wrong. It was just I was looking and I was like, he does this like twice, so I'm not sure.
Wait, did I say power equals IR twice? I said it was equal to IR
Well, no,
twice?
in the lecture you write power equals I1 times R1 plus I2 times R2, so on and so forth.
Yeah, sorry, it's I1 squared R plus I2 squared R. Yeah, that's my mistake.
Okay.
Okay, there you go. So you do RREF on this. And this is what you get. Yes, you can also do V squared over R. Correct. If you're comparing things that have the same current. So if you're comparing things
in series. Alright, sorry, if you're comparing things in parallel, then you want to use V squared over R. If you're comparing things in series, you want to use I squared R. We did that with like the light bulb question. Okay, so here you go. So from this, you get that I1 is equal to 0.6 milliamps. I2 is equal to 0.4 milliamps.
Do I have it backwards, Maxi? Maybe. Oh, right. Wait. Sorry. Things in parallel, you want to use V squared over R because the V's cancel. Things in series, you want to use I squared R because the I's cancel. Correct. Thank you. Yes, you're right, Maxi. Yes, because you want to just compare the resistances. All right, and what were they asking for here, dog? Oh, the resistance through the, what is it? the current through R1. So that should just be 0.6 milliamps. Which, yeah, is the correct answer. Nice.
Good job.
This is what I'm supposed to be good at. You are good at it, Maxie. Good. Maxie, what are you doing after? What's next, dude? That's been the funny thing in my chat now. Asking. Don, another awesome person in our stream, just graduated with his master's degree in math. And so we're asking what he's doing next. I'm curious what a electrical engineer, I guess, is looking for these days. TI? Dude, fuck yeah, TI. That's the calculator, dude. I got the TI Gold Edition. Okay, Jack. Was this good? Yeah?
Yeah.
This makes sense? We
Yeah,
did like
let
a
me
deep
see.
dive.
Have any other questions?
Yeah.
That makes sense. That makes sense.
We'll also have office hours tomorrow, and
Yeah.
I can
Well,
extend it out.
Like for same homework question 11 and like 12, are we going to see something similar in like the diagrams of circuits?
Let me see.
Because it has this like triangle shape that like confused the hell out of me for a little bit.
All right, let me see. Which number? 12?
11 and 12. Like you'll see the diagrams.
Okay. Yes. Yeah, these are cool. I like these.
All right, probably on the exam.
Yeah,
Got it.
probably on the exam. Yeah, go look at question 11, question 12.
Question
30 seconds.
1,
Nice.
question 12 or question 11 and question 12?
Wait, why are my diagrams not showing any? Oh, because I'm at the practice questions now. Sorry. Dude, this is such a funny one. I'm not going to put this one on the test. I remember someone asked this one during my stream once. the cube of resistors.
No, God! No, God, please, no! No! No!
I mean, I guess it's doable because like what
It is. It is totally doable. It's just it's kind of a bitch to like unwrap it and figure out like what's in parallel with what's in series with what, and I feel like yeah, it's kind of a pain.
Okay, that sounds fun.
You want to try it, Maxie? Go for it, Maxie. I think you can do it with mesh analysis for sure. I think the way to do this one is to use mesh analysis, or I think the answer is maybe there's something with Kirchhoff you can do. I forget.
Actually, how would you do that one? That one.
Don't worry, it's not on the exam.
You can't
Don't
even
worry.
you can't even break the lines.
Yeah, you can't. Yeah, I think you have to do Kirchhoff laws. You also you have to do. Man, it is a pain. This one is a pain to do because these two are like this is in series with this, but then this is in parallel with the It's like a bunch of voltage dividers that are happening. The homework one for the 2 batteries. What's the homework? So which AQ? Which homework question has 2 batteries on it? Sorry, I'm just trying to find it. Yes, exactly. Yeah, no, it's something with the corners. I remember that. Someone asked us that question, I feel like, at some point. Oh, okay, so sorry. By the 2 batteries, AQ, are you talking about this one? The one we literally just did? Where you have a battery here and a battery here. Yeah, this one right here. Yeah. We just did it. That's what this whole thing was. The quick and dirty way to do it, sorry, not the quick and dirty way. You're okay, AQ. It's okay. Yeah, so this is the whole derivation we did for it. In reality, if you want to solve this, you really just have to do 2 loops. You do this loop. And notice how this loop ignores this battery. We don't even care about it. And then we also do this loop. Okay? Which only includes this battery, doesn't include this one. And then we used... So you come up with loop equations for the 2 of those. And then you look at what the juncture law is for here. So...
So back to the linear system of equations stuff. So I need the same number of linear equations in my system of linear equations as the unknowns I'm trying to solve for. Is that right?
Yes. What'd you get, Maxwell? What'd you get, Max? Tell me. 5-6. That is correct. 5-6 is correct. Trying to see where it was. It was one of the practice questions. Yeah, nice.
Nice.
Good job. That was quick. That was quick for you, Max. Okay. Any last minute things on these, Jack? I want to like run the gym, like make sure I get some exercise today. But
let me see. I think my last question would be like number 15.
Let's see.
I'm not gonna ask you to solve the whole thing. I'm just wondering, in this situation, since I have like 3 separate loops.
Yes.
And do I ever want to try to solve for a loop on the whole outside of the circuit?
Ah, okay. I see for this one.
Because one of the loops I was originally using was just a loop from the whole way from voltage 1 all the way on the outside rim till its negative terminal.
Yeah. So, what were they asking for? Was it... they want the total power dissipated in this whole thing? Yeah. Yeah, so in order for that to be calculated, right, you need currents for all 3 of these things, right? Yeah. So you have 4 things you don't know. So there's like 4 unknowns.
When don't I have 5 unknowns? Because 5 currents?
Well, I mean, do you need I5? Because look, I5 only applies to this leg. Right? Anytime the current splits, it's no longer the same current. I got you, Maxie, yeah. Yeah, I remember it being like...
At that junction to the right of R3,
yes.
Technically, I'm breaking up 2 currents.
So technically, you have I4 coming in here.
Yeah.
And you have I3 coming out here.
Yeah.
Yeah.
But wouldn't I5 be its whole new different current?
It would be. Yeah, I5 is a whole new current.
So that would be 5 unknowns, no?
But do I need I5? Because I want the power dissipated, which means I just need I2 for this, I1 for this, I3 for this, and I4 for this.
Okay, because so I don't need...
Yeah,
I5 have resistors.
Exactly. The only thing I care about power being dissipated is through the resistors, and so I only care about the currents that are associated with those resistors.
Okay.
So I think how this works, you'll have one loop here, you'll have a second loop here, you'll have a third loop here. Notice how I5 won't show up in any of these loop equations, because I5 doesn't go across any resistors.
Okay.
And then I think you can use like this juncture or this juncture to get your 4th equation, and then you're golden.
Oh, okay. Because when I tried solving this one, I used 5 equations because I solved for whatever I5 was.
Sure. And you totally can solve for I5. It turns out I5 is just going to be equal to I4 minus I3. It's kind of, it's like a nothing burger. It's kind of silly to solve for it, right? Because current out, which is I5 plus I3, is just equal to I4. So it's like, all right, yeah, duh. So I5 is just I4 minus I3. It doesn't show up anywhere else, right? So in fact, technically, right, this is I2 coming through here. This is a new current. This would be I6. I have no clue what this is. And then technically this is also... Okay, sorry. This one is I4 though. Right? Because this part of the current is still...
Yeah, because when I was doing this, I was like, I could potentially add so many more currents here, because...
Well, you can only really add one more current. That's the key thing to recognize, right? Currents only change when there's a split. I4 refers to this, which means it extends out to here, and then extends out to here. As long as the current hasn't split off, it's the same in that line. That's like why I3 is here. I2 is all the way here. And then technically, I guess you got I1 here. You got I5 here. And you have, I don't know, I6 here.
In each linear system equation, it should probably have at least one unknown in it that I can use to solve. Or is it just like, it doesn't even have an unknown, but...
Oh, I mean, it'll have a ton of unknowns, right?
Well, I'm just wondering, how would I know, like, how do I see and know that this is a linear system equation I want to add to my system?
Oh, yeah, it should contain variables that you're curious about, right? So, like, this technically would be useful because it includes I4 and I3, but you don't really care about I5. Maxwell's getting it already, dude. Maxwell's like, is it 34 watts? It is 34 watts. Good job, Max.
Good job.
Max is just out here like speed running E&M questions. Akert says, for flux and potential stuff with integration, what should we practice? I want more practice with those techniques. Yeah, any of the homework questions, I think. There's some good homework questions. The exam had some really good integration practice stuff.
Yeah.
Right? We did integration. You did integration with a sphere. You did integration with a cylinder.
Nice.
That stuff is all very useful. Oh, nice. We got another follow. Thanks for the follow. 2540. Circuits is my favorite. Yeah, I love circuits. I'm a huge fan of circuits. The only thing I didn't like was like transistors. I never liked when they're like, oh, well, this is VPP, this is V out, this is like V, like doing op amps. Op amps were like bane of my existence, dude. Because it just felt like a bunch of like random equations. Yeah, like this shit. Well, this is crazy, but still. I remember having to like help students out with this stuff. And I'm just like, oh my god, please stop.
Emotional, damn it!
Or like, was it?
All right. Thank you.
Okay, you're all very welcome, Jack.
What time is your next office hours tomorrow?
Same time as normal.
All right. Thank you.
Yeah, you're welcome, dude. Yeah, this stuff, dude. Max, you probably had to do this. This stuff like hurt me.
Oh no.
Shit, not good.
Stuff hurt me a lot. Okay, cool. All right, I'm a little bit over time. Let's close out the stream. All right, thank you everyone for coming to Actual Education Office Hours. Try cascading op amps. Yeah, no. No. Anyways, thanks for finding the stream, Maxie, by the way. Yeah, if you want to... So we do this pretty regularly. I'm teaching a UCLA physics course over the summer, so that's why I have primarily physics happening this week, because it's final exam week for them. But we've been doing this for about 5 years, and I do all sorts of tutoring in courses. You're probably above the level at which I could help you at because like I don't know like senior level EE stuff, but if you have anyone else that needs help with like, I don't know, even like chemistry or like math, we do a lot of stuff. The ideal transistors, yeah. So anyways, the website again for everyone that is just joining us or just found us, www.actualofficehours.com. Oh, you're good. Yeah. Great, Maxie. I smelled submit wrong. Ooh, there we go. Dude, excuse me. Oh, okay. Submit. There we go. Great. So we have our schedule there. You can see all the times that we're streaming. So I will be teaching my last lecture of the summer. Oh, you subscribed? Thanks for the sub, Maxie. UG, dude. Appreciate it.
That's dope.
That will be my last lecture will be tomorrow at 12:30, and then we will have office hours again at 5, and then I'm gonna take probably the weekend off just to grade, but then we'll be back at it next week. So we'll be right back. No, we won't be right back. We're already here. So yeah, come on by, have fun. Shout out to all the great people that rated us today. We had Dawn, who just graduated. Congrats, Dawn, on graduating grad school. We had Obi, the ODE master, and we have a bunch of other friends. If you want to learn more about like E&M stuff, Zach's doing kind of a study group tomorrow, starting at 11. Penn Center's doing real analysis at 1 o'clock. And then Friday, I think we'll have a chess tournament in the evening. I'll announce that tonight. And then he's also doing abstract algebra, so cool. All right, let's go raid someone. Let's go say hi to some of our friends on Twitch. You want to play chess? Yeah. Well, it's in there. So if you're in the Discord, Maxi, you'll get like an announcement if you have like the chess player role. I'll ping everyone in the server for it. I do that for like big events. But we'll do a chess tournament on Friday if you want to come play. I say like you don't have to be good, you don't have to be great, you don't have to be terrible. Everyone has kind of like a chance to win some prizes. Just come on by. And the only way to get better at chess is to play chess. That's what I say. All right. Who else is on right now? Oh, a lot of people streaming. A lot of people doing video games, though. Ooh. Wednesday science communication with Rocco Doctilus. Let's go say hi to Rocco. I don't think I've ever rated Rocco. Yeah, I'm like average too, exactly. It's fun. It's just fun to play, though. Yeah. Some of the students are really good. And I love getting humbled. Okay, cool. Enjoy the rest of your Wednesday. We'll see you Thursday. Peace.
Do you know that there's a massive environmental component and a massive epigenetic component? Nutrition. Nutrition also does a lot to contribute to height. That's not genetic. So yeah, it's a nice little comparison case. Yo, actual education. Thank you so much for the raid. I do appreciate that. We are actually nearing the end of the stream, so you kind of came in at the tail end as I'm wrapping things up and the sort of like take-home messages and stories. But welcome on in. I really do appreciate it. Thank you so much for the raid. Thank you for sharing your community. I do appreciate it. But